Hello, this is Team17 presenting Contextual Bandit problem for AFM. AFM instruments are used to obtain high-resolution images of surfaces at an atomic level. It records surface topography to atomic level precision by moving a tip back and forth across the surface. The tip scans like a needle on a record. As it gets close to bumps or dips on the surface, the tip moves up or down slightly. A laser beam watches this movement, and the computer tracks how much the tip bends. By measuring these bends, the AFM can build a precise map of the tiniest bumps and valleys on the surface, much like feeling braille with your fingers. The map lets scientists see the surface in incredible detail, even down to individual atoms. It has several parameters that can be adjusted. However, 4 of these have a direct effect on the quality of the scan. This requires a lot of experience and trial and error to get it working properly. So we are using a contextual bandit algorithm to help automate hyperparameter tuning for AFM machines. Contextual bandits learn the most rewarding action based on contextual information to optimize its decisions. The contextual bandit problem can be seen as a single-step reinforcement learning, which not only optimizes decisions based on past observations, but also personalizes them for every situation. We are using this previously established approach to help solve our given problem. Ideally, this can turn a long and tedious task into something that can be completed with a push of a button, therefore making this type of work accessible to all. We decided to use a contextual bandit to help pick a balance between choosing parameters that the model thinks is correct and ones that are more experimental. Contextual bandits are kind of like a game, but instead of playing just one round, you're playing many rounds. Each round you're giving some information about a situation, and based on that information, you have to pick one option out of several. There is a twist though. You don't know for sure which option will give you the best reward in each situation. So you have to make an educated guess. After you pick an option, you get a reward, but you don't get to see what the rewards for the other options would have been. Over time, as you play more rounds and gather more information about the situations and the rewards, you start to figure out which options tend to give you the best rewards in different situations, so you get better at picking them. In real life, contextual bandits are used in things like online advertising or personal recommendations, where you're trying to figure out which ad or recommendation will get the best response based on different context. So we also implemented a neural bandit. This is a fully connected neural network with atom optimization. The network outputs an action that corresponds to 4 AFM parameters. Whenever it does this, there's a small chance that it'll just pick a random action. It uses the reward from that function compared to the optimal reward to update the model. We also used an epsilon greedy agent. This agent will keep track of estimated reward values, and it will choose or will balance choosing between a random action and picking the highest estimated value. So now for our results and discussion. Figure 3 and 4 show how cumulative rewards and show our cumulative rewards and regret of our model, which is the neural bandit compared to the baseline model, the epsilon greedy. Figure 3 has a continuous action space, and Figure 4 has a discretized action space. So the neural bandit performs better both with continuous and discrete space. The rewards for the neural bandit are more than the baseline, which just means that the actions chosen are given higher rewards. That being said, the regrets that we see in all of our cases are a little high, so we still have to reduce this. Figure 5 and 6 here just show how the model performance changes when the action space is discretized. So this is just showing that having a huge action space in the model helps it make better decisions, but the problem is that's not practical or feasible when deployed on a live instrument. In conclusion, we have implemented the contextual bandit problem with epsilon greedy to help optimize AFM parameters to increase the image quality. When implementing this, one of our biggest challenges was discretizing our action space. If we have too many actions, our space essentially becomes continuous, which we don't want. The next steps we have are to continue to refine our model and improve the performance. Once this is done, we'll test it on a real AFM machine. This will allow us to see how our model works in a real-world setting, and if it does work well, operators will be able to improve their performance tremendously.